Okay, so let's begin the lecture. Okay, there's a question. Okay. Yes, this is the right place. Yes. Okay. Okay. So again, the format is that raise your hand if on Zoom. That is, if you have a question. Okay. Okay. I guess some people from the other chat room are still coming, but okay. I guess we'll start. So okay. So this is lecture 17. Let me just move this away. Okay. So this is lecture 17. Okay, I'm not sure where that came from. Wait a second. I can't see my eraser. Just a second. Sorry. Okay, where's my eraser? Okay, wait. Okay, good. So I can see the eraser now. Okay, sorry about that. So so this is lecture 17, and we're going to continue talking about eigenvalues and eigenvectors. Wait, let me open the Q&A box so people can ask questions. Okay, participants. Okay, so so what did we do last? Well, last time we talked about diagonalization. We made this connection between diagonalization and eigenvectors and eigenvalues. So we said that if a matrix, an n by matrix, has n linearly independent eigenvectors, which are linearly independent, and that's important, with corresponding eigenvalues, then you can use this to diagonalize the matrix. So find a similarity which shows that this is similar to a diagonal matrix. So then what you do is you can make the following matrices: a square matrix P invertible containing the eigenvectors, and a diagonal matrix D containing the eigenvalues. And then we verified, and this was just an algebraic check, we verified that this satisfies A equals PDP inverse. And the meaning of this is that A is similar to a diagonal matrix, which means that in this basis of eigenvectors, the matrix of the linear transformation corresponding to A becomes diagonal. So we refer to this is what it means to be diagonalizable. And the upshot of this was that in certain problems, this led to a great simplification. So for example, we had some problem where we wanted to compute some high power of A. And this was maybe a hard problem. And the reason it was hard is that when you take powers of A, all of the coordinates interact, right? But by diagonalizing A, we observed that, well, you can write this product as just PDP inverse times PDP inverse, PDP inverse, K times, and now all these P inverse P's in the middle cancel. And you're just left with P times D to the K, P inverse. And this times, again, your vector X naught. And then after you do this change of basis, this D to the K problem, this is an easy problem because it's decoupled. the coordinates don't interact. So you have n non-interacting coordinates. And so I ended the lecture with a specific example. So let's just recall what that was. So in the last lecture, there was spheres and and here, once we encoded it as a linear algebra problem, the setup was that there was some matrix A, which looked like this. There was a vector x naught, which was literally the vector 30, 10. This was some initial population of snowboarders and skiers. We were interested in computing some high power of x naught. And this, it looked like we had to do a lot of arithmetic. I believe the power was just 10. And so what we did is we diagonalized the matrix. So we computed eigenvectors, which turned out to be 2, 1, and 1, 1. Let's call them V1 and V2. And eigenvalues, which turned out to be 3 halves and 1. Okay. And then we observed that you could turn this powering problem into just raising the eigenvalues to the 10 power times x naught. And I could compute the inverse and just do the matrix algebra, but maybe a more conceptual way of explaining what this does is, well, you can expand this vector x naught in the eigenbasis, right? So you can form this basis B out of eigenvectors. Once you expand the vector in this basis, it turned out it was equal to 20 times V1 minus 10 times V2. You could find that by row reduction. And so another way to view this product is, well, this is equal to a to the 10 times 20 times V1 minus 10 times V2. And then by linearity, that's just 20 times a to the 10 V1 minus 10 times a to the 10 V2. But now I use that these are eigenvectors, right? So a just acts like scalar multiplication. So a just, every time you multiply V1 by a, it multiplies it by this number 3 halves. So this is just 3 halves to the 10 V1 minus 10 times 1 to the 10 V2. And then I can, calculate what that is. So, okay, so I actually did this. So this is 20 times some number that's close to 57. It's not exactly 57. And V1 is this vector 2, 1 minus 10 times just 1 times the vector 1, 1. And then if you calculate this out, you could do the arithmetic, but the key thing I want to point out is that this number is much bigger than this number. And the reason is that the 3 halves eigenvalue got raised to the 10, and it was some number bigger than 1. And so it grew exponentially, actually, is what this is called. And so whatever this is, I didn't calculate it, but there's going to be something that's pretty close to, this term is much bigger than the second term, right? So it's going to be pretty close to just 20 times 57 times times V1. And so in particular, not only did I manage to calculate the answer, but I managed to detect some phenomenon that was happening as I take repeated powers of this matrix. And the phenomenon was that the coefficient of V1 grows exponentially. In K, right? The more powers I take, the higher power of 3 halves I get, which is growing exponentially. And here, this stays the same. Because it's an eigenvalue that's equal to 1. I could raise it to whatever I want. It's not going to. And so apart from just being a calculational tool, eigenvalues explain the dynamics of what happens if you take a vector and keep applying this matrix. So I'll just say here's real in the context of taking, starting with some vector and repeatedly multiplying it by the matrix. And this is something that occurs a lot in nature. Well, if you have an eigenvalue that's strictly bigger than 1, then after k iterations, this is going to be this is going to be raised to the power k, right? So the corresponding eigenvector grows like lambda to the k, which is exponential growth in k. So somebody had a question. Yes, do you have a question?
Hi.
Oh, hi.
So I just had a question about when you multiply, let's say like a squared by the vector, wouldn't it be like a times a of the vector, and then it only gets applied once? Like, why does it get applied to the actual vector 2 times or 3 times, however many times?
Oh, well, I mean, well, that's what a squared means, right? So a squared x means a times x.
Yes.
So going back to this picture, I applied a 10 times to my vector x naught, right?
Yeah.
And the key thing I wanted to emphasize is that means I apply a 10 times to v1 after changing into the eigenbasis.
So it's not a to the 9th times the eigenvalue v1.
No. So okay, let's work it out. Let's think about it. So a times v1 is just 3/2 times v1, right?
Yeah.
A squared times v1 is a times 3/2 times v1, which is 3/2 squared.
I see. Yeah.
Yeah, so that's a good point. In general, applying a k times to an eigenvector will raise the eigenvalue to the k.
Okay, thank you.
Yep. Okay. And by the way, I might as well add that each step of what I did here corresponds to a step in the factorization, right? So first I switched to the eigenbasis. That's what P inverse does. Then I raised the diagonal to the power. That's what d to the 10 does. And finally, I switched back to the standard basis. That's what P does. So P dP inverse, or P d to the 10 P inverse, is exactly this process. Switch to the eigenbasis, raise the powers in the eigenbasis, which is easy, and then switch back to this. Yes. Do you have a question?
Yeah, sorry. I was wondering, what is x naught, and like how did you get it? Like, what does it represent?
It came from some skiers and snowboarders thing in the previous lecture.
Okay. So it's the initial condition, right?
It's initial condition, yeah.
Okay.
Initial condition if you're thinking about dynamical systems. But there are many other settings where this happens, as you'll see later, that you're looking at just powers of a matrix times a vector. This can be used to describe many physical processes. Okay.
Okay, thank you.
Is that good? Okay. So an eigenvalue bigger than 1 corresponds to exponential growth. An eigenvalue less than 1 corresponds to exponential decay. Right? If you have a number less than 1 and you keep raising it to higher and higher powers, it's going to go to 0 exponentially fast. If you have an eigenvalue equal to 1, this corresponds to equilibrium. And if you have an eigenvalue equal to -1, this corresponds to oscillation. Right? So for example, if I have a matrix with a +1 and a -1, and I raise that to the k and multiply it by some initial vector x1, x0, well, the answer is going to be, I mean, this is a diagonal matrix, so the eigenvectors are just a standard basis. I'm just going to have, this is going to be x1, but I'm sorry, I shouldn't call this x0, let's call this x2. X2 is going to be oscillating depending on whether k is even or odd. Okay. Yes. Do you have a question?
Yeah, isn't the second one supposed to be less than 1 but greater than 0, and the last one supposed to be less than or equal to -1?
I'm sorry. Yeah, you're right. You're right. So thank you. I'm assuming here the eigenvalues are positive. Actually, yeah. You know what? Let's just put absolute values here. That's another way to do it. Okay. So even if it's negative, if it's less than 1, its magnitude is going to shrink exponentially.
Mm-hmm.
And if it's negative, it's going to oscillate and shrink exponentially, but it will shrink exponentially.
Okay, thank you.
Yeah, thanks for the, I should have said that. So that's one interpretation of what the eigenvalues mean. We'll see many more as the course progresses. Okay, so we also discussed similarity, but there's one question that we didn't address. So for most of the concepts that we did in the course so far, we discussed how to check when matrices satisfy that, right? They are similar, right? So, I mean, diagonalization is a process that allows you to check whether a matrix is similar to any diagonal matrix. But what if I give you two matrices and ask you, well, are they similar? How do you do that? So if A and B are diagonal, or if they're literally diagonal matrices, then it's pretty easy. You can check that they're similar if and only if the entries are the same up to permutation, by which I mean up to order. Okay, so this is an easy exercise which I'll leave for you. You can just it's a good exercise. You should do it just to make sure you understand the definition of similarity. So if two diagonal matrices have the same entries, but maybe you switch the order, then they're similar, and that's the only case. This extends to diagonalizable matrices. If A and B are diagonalizable, so remember, diagonalizable means A is similar to some diagonal matrix, and B is similar by some other similarity to some other diagonal matrix, where C and D are diagonal. Well, if they're diagonalizable, then again, it's an exercise to check they're similar if and only if the eigenvalues are the same. And that means multiplicity. And again, up to permutation. So what's the proof of that? Well, I might as well tell you the proof. Oh, I see. So there's a question. Yep. Do you have a question?
Yeah, sorry, I just don't quite understand what you mean by up to permutation.
Okay, yeah. So let me say here. So what I mean by this is 1, 2, 3 is similar to 3, 1, 2. So I mean you can swap the order. So why is that? Okay, we might as well construct the P that so let's say this is A and this is B. Can you think of what the P is that shows a similarity between A and B?
If you just hit it by something that would scale 3 by like a third, and then I guess something that would just change the numbers into each other.
No, actually. Okay, so this is a good point. So remember, a similarity means okay, so let's maybe do it here. So the question is find some Q such, or P, let's call it, such that A equals B, B, P inverse. So one proposal was, well, just find, so let me just maybe write it. Okay, let me write it here. So the proposal was, well, what if you just take P that does P of E1 equals 3E1, P of E2 equals half E2, and P of E3 equals, I guess, 2/3 E3? Is that what you're thinking?
Yeah.
Okay, so the, okay, so, okay, so let's check what happens if you do this. So now if you look at P, B, P inverse, what will you get? Well, you'll get B, but now you multiply it on the left by P. So this, so okay, well, you multiply it on the right by P inverse. So what you'll do is you'll divide by 3 here, but multiply by 3 here. And here you'll divide by a half, so which means multiply by 2. But then you'll, on the other side, you'll do the opposite. So you'll multiply by a half. And then here you'll multiply by 3 halves, but divide by 2/3. Multiply by 2/3. So you actually won't do anything. This actually doesn't work. Do you see what I'm saying? That this particular choice where you just rescale everything actually does not work.
Okay, that makes sense.
So I'll write the thing that does work. So this does not work. I'll write the thing that does work. The thing that does work is really simple. How are these two matrices related? Well, you just reshuffle the coordinates from A to get to B, right? So let's just define the transformation that just does that. P of E1 equals E2. P of E2 equals E3. And P of E3 equals E1. So that's called a permutation, because all it does is it reshuffles. It just changes the order of the coordinates. Right? And now if you go back to the definition of similarity, well, what does similarity mean? Similarity means that the two matrices represent the same linear transformation in different bases, right? And what are these two linear transformations doing? Well, they're stretching one basis vector by 3 and stretching one by 1 and stretching another one by 2. But if you change the names of the basis vectors, they're both doing the same thing. And so that's what I mean by permutation. But this is the similarity. Does that make sense?
Yeah, thank you.
Yep. Yes, do you have a question?
I would like, so in this case, P would be, well, let's go by row. 0, 0, 1, 1. Let me see. Am I 1, 0, 0, 0, 1, 0? I believe it.
Okay, I see what you're saying.
Thinking about.
I think the right one might actually be this. Inverses.
Okay.
One of those.
Yeah.
You should check which one it is. This is something I always get confused about this day. the one that that shuffles them in the right direction. This is the difference between applying it to A and applying it to B. I did the calculation for applying it to A.
Yes, because what it does is that, let's say A is in the columns of A are in standard, right? And then B is in its own thing. So
yeah,
I believe that's the way to think of it.
Yeah, that's right. So so okay, I mean, since this has become sort of I mean, since I can see how you may be confused about this, let me just do it again. So let me erase this for now. Okay. So let's check this. Let's check this. Right. So let's compute P inverse A P. Right.
Yes.
So okay. So actually, you know what? Instead of doing this in matrix algebra, I'm going to try to do this more conceptually. Let's make two bases. So there's a standard basis E, which is E1, E2, E3. And then there's the B basis, which actually has the same vectors, but in a different order. So it's going to be E3, E1, E2. Okay. And what I want to check is what's the matrix of A in the B basis? Right? What is that? Well, so that's going to be A E1, A times E3 in the B basis, right? Second column is A times E1 in the B basis. And the third one is A times E2, the B basis. Okay, what's A times E3? Now I go back to this definition. Well, A times E3 is just 3 times E3, right? So that's going to be 3 times E3. 3 times E3 in the B basis is a vector 3, 0, 0. What's A times E1? Well, that's just E1, because A just multiplies E1 by 1. And in the B basis, that's the vector 0, 1, 0. And what's AE2? Well, that's gets multiplied by 2. But in the B basis, that's a vector 0, 0, 2, which equals the matrix B. Okay. And so therefore, the right similarity, but this again is equal to the matrix of A, the standard basis, times this change of basis, right? So okay, so that's the similarity, and that's the thing that's yes, do you have a question?
Yeah, I'm sorry. I just didn't entirely understand the change of basis. Would it be okay if you went over how you ended up with the basis? I mean, A in the B basis again, just once. I'm sorry.
So the reason this is confusing is that a basis is actually an ordered list of vectors. So maybe it would be less confusing if I gave these some new names. Right? There's nothing preventing me from making a new basis B1, B2, B3, which literally has the same vectors as the standard basis, but in a different order. So now I'm just following the formula for writing the matrix of A in the B basis. In each column, I evaluate A on the B basis as input vector, and then write the output in the B basis. Right? So for example, what's A times B1? Well, that's just A times E3, which is 3 times E3, right? Which is otherwise known as 3 times B1. right?
Okay.
So that explains the first column. Does that make sense?
Yeah. Thank you.
Any other? This is a admittedly confusing point because you always have to check whether you're doing P or P inverse, hard to remember. But anyway, this exposes another important point, which is an important class of invertible matrices is just permutations, things that change the order of the basis elements. And they actually come up a lot. Okay, so for diagonal, they're similar if and only if they have the same entries up to permutation. It won't prove this. If and only if they have the same characteristic polynomial. Okay, which is the same thing as saying if and only if they have the same eigenvalues up to permutation. So in particular, if I have A and B diagonal, A is B, C, D inverse, B is Q, D inverse. Then since similarity is, I mean, it's easy to check A and B are similar if and only if C and D are similar. But then what do C and D contain? They contain the eigenvalues of A and B, right? So by what we did previously, you get that they're similar if and only if they have the same eigenvalues of. Any questions about that? Yes.
Do we need to know why, like the proof of why it's if and only if C and D are similar?
The proof of why A and B are similar if and only if C and D are similar?
Yes.
Yeah, I think it's a homework problem.
Okay, got it.
It's not hard. It just follows from the definition of similarity, but I think it's a homework problem.
Cool, thank you.
Any other? Yeah. Hello?
Yeah, hi. Okay, I have a question on the previous slide.
Mm-hmm.
How did you know that E3 was B1?
I just defined it to be that way.
So you're not getting that from A and B above? Like
No. Oh, I am, right? Because if I look at A and B, right, then I'm asking, well, you know, I want to find a change of basis so that B is the matrix of A in that new basis, right? That's what similarity means. And I can tell that B is pretty much doing the same thing as A. It's just stretching one coordinate by 3, stretching 1 by 1, and stretching 1 by 2. The only thing is it changed the order, right? So accordingly, I defined a new basis, which is literally the same basis, but different order. So how did I get this basis? Well, I observed that, you know, the first element of A in the standard basis, oh, wait a minute. Have I messed up here?
No.
Okay, yeah, have I messed up here? Let me see. So I defined, you're asking how did I get this B basis, right?
Right.
Okay, I'll tell you how I got it. How I got it, here's my thought process for getting it. I looked at what I looked at, so ultimately I want to set it up so that the matrix of A in some basis is equal to B, right? Now the first element of the diagonal matrix B is 3, right?
Right.
So I want that to correspond to a basis. I want that to correspond to a vector that's multiplied by 3 when I apply A to it. So what vector gets multiplied by 3 when I apply A to it? Well, E3. The 3 is the last entry of A. Does that make sense?
Because it seems like we're looking at more of the eigenvalues rather than the basis vectors, if that makes sense.
Well, okay, so for a diagonal matrix, the diagonal entries are the eigenvalues,
Mm-hmm.
and the standard basis vectors are the eigenvectors.
Okay. Okay. That
So,
makes sense.
I mean, okay, you know what, actually, maybe it'll be, I mean, in general, what you would do, so, okay, maybe this will be clarified if I say what you would do in general. Sec. In general, what you would do is you would just apply the change of basis that goes from one eigenvector basis to the other. So if these have the yeah, so it's a good thought. So what I did here is I actually paired up the eigenvalues, right? That's how I know that. I mean, that's somehow the meaning of the linear transformation, that this has eigenvalues 1, 2, 3, which are acting in 3 different directions, and I want to find a p that turns those into the directions that get multiplied by, 1, 2, 3, but in a different order in the b basis. Does that make sense?
Yeah, I was also wondering if you could just find, like, since it's for similar matrices, if you do AP equals BP and then somehow find P, would that be possible?
That's a good question. I'll answer that in a moment. Hi, do you have a question?
Yes. I believe that the proof of the, well, first the proof that if a matrix, if two matrices are diagonalizable, I believe that it's true that their eigenvalues carry over.
Yeah. Oh yeah, we proved that in the last lecture.
That was in the last lecture. Okay.
One direction we proved, right? If they're diagonalizable, then the characteristic polynomials are the same.
Okay. And secondly,
in the last lecture.
And back to the last slide. I think the theorem says like up to entries are the same up to permutation. So
yeah,
by up to, is that mean?
That means you can change the order to get one from the other one. That's all.
Okay. So basically, A and B have the same entries, but are in a different order.
That's right.
Okay.
I mean, this becomes a little bit subtle when there are entries that are repeated, right?
Yes.
So it just means they have the same algebraic and they have the same multiplicities.
Yes.
Yep. Okay. Yep. Any question?
I think someone might have asked something about this already, but on this slide, could you explain why you changed from doing P E1 equals E2 to P inverse E1 equal E2? Like, I wasn't really sure what the difference.
Well, the difference is, okay, so P, okay, so the reason is because my definition of similar is, sorry, why is this writing? Okay, similar according, wait. Okay, so similar for me was that A equals P, B, P inverse, right? What I ended up deriving down here is, okay, so let's explicitly write down what this P equals to B matrix is. Well, it's a matrix that contains the columns of B as it contains the basis vectors of B as its columns, right? So it's a vector matrix 0, 0, 1. 1 0 0 0 1 0, right? So the reason I wrote P inverse is that, well, simply one of them is correct and the other one is wrong. It's not the same. It's not the same thing to map. So this matrix maps E1 to E3, right?
Mm-hmm.
But what's written up there maps E1 to E2. So actually, what's written up there is P inverse, not P.
Okay.
So another way to put it is P maps E1 to E3 and E2 to E1, right?
Yeah.
But that means P inverse maps E1 to E2.
Okay.
And that's what's written up here.
Okay.
Right. So I just ended up writing the inverse of what I needed to write.
All right.
Which is why.
Thank you.
Okay. Okay. So that's all I want to say about similarity. Sorry, I meant for that to be a 10-minute thing, but I guess it turned into a big thing. But okay. So now I want to move on to this question of which matrices are and the answer is not all of them. So here are some examples. What is this matrix? Sorry, seen before. So this corresponds to a rotation by 90 degrees. And this, the characteristic polynomial we observed, was lambda squared plus 1, which has no real roots. So this one doesn't have enough eigenvalues. Okay. Another bad thing that could happen is have a matrix like this, which we also saw earlier. The characteristic polynomial of this matrix is okay. It's actually just lambda squared. I'm sorry, it's lambda minus 1 the whole squared. So it actually has an real eigenvalue of 1. But if you compute the null space, which is just the null space of this matrix, this is the span of just this vector. And so you don't have enough eigenvectors, right? So not enough eigenvectors. So these are two bad things that can happen that prevent diagonalizability. So it turns out that here there's nothing you can do. Okay, you cannot diagonalize a matrix. There's no modification of the definition of diagonalizability that allows you to do this. But here you can fix this by considering complex numbers. So what I'm going to do is now talk about this. And before I do that, I want to introduce you to complex numbers, because many people may not have thought about it for a while. So to put this in context, I want to tell you about a history. Okay, so first, I don't know when, I mean, maybe thousands of years ago, people invented positive. Okay, and they were happy with that for a while because you could use that to count things. Yes, is there a question?
Yeah, I just wanted to note that like your mic keeps going in and out. Is it possible for you to stay like
sorry.
in the range?
Sorry.
Yeah. Thank you.
Okay, so first people had positive integers. You use them to count things, people were happy. But then people discovered a problematic equation that they couldn't solve just given positive integers. And the equation was, well, one example of an equation is just, x plus 2 equals 0. So what's the number so that when you add 2 to it, you get 0? Well, there are no positive numbers that satisfy that equation. So this led people, on the other hand, this problem comes up, it's a sensible question to ask, right? So this led people to invent the integers. So these are systems here. And then people were, this means that now you have negative numbers, right? So positive, I mean, positive integers and 0. But now integers, you have negative numbers. And this also seemed good for maybe a few hundred years. But people were kind of bugged that, again, there were very simple questions about integers that you could ask that didn't have answers. Right? So you could ask a question like, well, what's an integer satisfying 2x equals 3? Well, there are no integers, right? Satisfying. So again, motivated by this equation, people invented the rational numbers. In other words, fractions. And this was pretty great for a while. This actually lasted until maybe early AD or maybe around 400 BC or something like that. But then there were still equations like this that didn't have a solution. And things became really intense around irrational numbers, for example, in ancient Greece, because there was a secret cult of people who believed that irrational numbers exist, but they were considered heretics by everybody else, and people were, literally burned at the stake or, thrown off a ship for suggesting that there could be other numbers, namely irrational numbers, which can be used to satisfy such equations. And this, okay, so I don't remember this person's name. So who was this person who was thrown off a ship? Okay, people were, executed for heresy. I don't know if, okay, maybe not heresy. I think it was BC. People were executed for suggesting this in Greece. And so then people invented irrational numbers, and this was fine for maybe 1500 years. But then there was still one very simple equation that did not have solution in rational numbers, which was this equation, which is the equation we saw on the previous slide, right? And so it took until 1600s with the work of Cardano in Italy to define an even bigger number system, which includes solution to this equation. And the complex number system includes a new number called I, which is the square root of -1, and it's defined to be the number that satisfies this equation. Okay, so every time you had some equation that led to an extension of the number system. And you might wonder, does this go on forever? But the answer is it doesn't. Complex numbers are the last word. There are no equations in complex numbers that don't have solutions. The complex numbers are really special in that they're the end of this, centuries-long quest for a number system in which equations have solutions. So before we proceed with this, yes. Yes, do you have a question?
I have a question, but I believe pi was discovered long before people decided to suggest that.
Why do we care when pi was discovered?
Well, it's important. It's a historical. You're right. I'm not sure when pi was discovered, but so I think pi existed as a concept for a long time. I think you're right. I don't know if people knew what kind of number it was. I mean, I can find something about this and send it to the class, but you're probably right. I'm not an expert on the history.
Okay.
Yep. Okay. Okay. So, so irrational includes things like pi, which also before. And there's an interesting history around this. But anyway. So, okay. So before I tell you about these, let me. So it's tempting to ask question, which is, are complex numbers real? Right? I mean, after all, this is called an imaginary number. And this is, in my opinion, an irrelevant question. The right question is this a useful mathematical concept? And the reason I think this is an irrelevant question is that, well, nobody knows if real numbers are real either, right? I mean, who knows if irrational numbers are real? But this is not a question that has a well-defined answer. Wait about it, but it's not a mathematically interesting question. And in general, I think the development of math was actually slowed down for a long time because people were stuck on this point, are they real? So I think they're actually more real than real numbers, if you study quantum mechanics. But there's no reason to be uncomfortable with complex numbers or to treat them as being more mysterious. So let me now just say what complex. So complex numbers, so there's a set of numbers of type a plus ib, where a and b are real numbers. And this contains the real numbers, right? In particular, if b is 0, you get all the real numbers. And the operations on these numbers are defined as follows. So you have addition. So this is a plus c. So that's just entry-wise addition. You have multiplication, which is just defined using the usual rules of algebra. So this is maybe goes by the name of FOIL. You know how to multiply two algebraic expressions with parentheses. You follow the same rules here. You get AC plus IAD plus IBC plus I squared BD. And this is the twist. The only defining feature of the complex numbers is that I squared equals -1. We've added this one number that satisfies that very special equation. And so now if you group the real and imaginary parts, you get AC minus BD plus I times AD plus BC. So by the way, this is called the real part, and this is called the imaginary part. And so, okay, there's a notation for this. If you write a complex number z as a plus ib, then the real part of z is equal to a, the imaginary part of z is equal to b, and a and b are real numbers. Okay. You can also divide you have a plus ib, c plus ib. Well, what's the ratio? The way you define the ratio is by multiplying by this number c minus id, the numerator and denominator. And if you do this, well, in the numerator, you get AC plus BD plus I times BC minus AD. And the denominator, you'll check, you get C squared plus D squared. So this only makes sense when C squared plus D squared is not 0. You can't divide by 0, just like with real numbers. So maybe another property to write down here is that the complex conjugate, Z bar, is just the same number, but with imaginary part flipped. And the magnitude of a complex number is square root a squared plus b squared, which is the square root of the number times its conjugate. Good job. That's how you define arithmetic on complex numbers. Okay, so it's basically just algebra with these expressions of type a plus ib, except I squared equals -1, and you define the usual arithmetic operations, but in this way. I should say there's a way to visualize these. So you can draw a two-dimensional plane where the real part is the x-axis and the imaginary part is the y-axis. And you can plot a complex number, a plus ib, as having, an a in the x-coordinate and b in the y-coordinate. You can think of it as a Cartesian plane. But the difference between this and R2 so can anybody tell me what the difference is between this and R2? Why don't we just think of this as R2? Yep.
Oh, I think it is that, well, you cannot simply, I believe that you can't simply multiply
exactly,
two vectors in R2
exactly.
and then get.
The difference with R2 is you can multiply. So you should not think of this as a vector space, you should think of this as an extension of scalars. Okay. So now the punchline, the reason we use complex numbers which was proven by Gauss when he was, I think, 18 or something like this. And here's what it says. It says every polynomial, every complex polynomial plus a1 lambda plus a n lambda n of degree n. And by the way, these coefficients are now complex numbers. They could be real, because real are a subset of complex. N roots. So that means you can always factor it in this way that we've wanted to. You can factor it as an times lambda 1 minus lambda, lambda 2 minus lambda, all the way up to lambda n minus lambda for some complex numbers. Lambda 1 to lambda n. So this is what's special about the complex numbers. And in our context, this means you can always have n eigenvalues. So it implies every characteristic polynomial of an n by n matrix has exactly n eigenvalues with multiplicity. Okay. So let's go back to our example and see how to diagonalize it. Our matrix was characteristic polynomial was this, which we now know how to factor. This is lambda plus I times lambda minus I. Right? Because lambda squared minus I squared is lambda squared plus 1. That's the whole magic property of I. And now, so okay, great. We have eigenvalues. They're distinct. What about eigenvectors? Well, to make sense of this, I actually now need, okay, is there, do you have a question?
Yeah, I was just wondering if you could go back to the last slide really quick.
Sure.
Thank you.
Yep. Okay. Okay. But what about eigenvectors? So now to talk about eigenvectors, I actually need to extend my concept of a vector space. Okay. So maybe not right. We will now extend all of linear algebra to so what do I mean by this? Well, I'm going to define some new vector spaces Cn, which are sets of, again, arrays of numbers. Now the numbers are complex. So I'm going to define Cn, and I'm going to define some operations on these vectors, same as before. So how do you add two vectors in Cn? Okay. And now how do you scale or multiply? Now this is the main twist. I'm going to allow you to scale or multiply by any complex number. Okay. So these are the operations. And now the point is the scalars can be complex. And what I'm going to do now is I'm going to observe, again, sort of in retrospect, that everything we did, we never actually used that the scalars were real. We just used that they satisfied the familiar rules of arithmetic. And the point is, can do everything we already did. You know, linear combinations, span, row reduction, pivots, all that stuff with complex scalars. So now I'm going to highlight this with my example up here, right? The example we've been looking at. So in our example, we have eigenvalues are. How do I find the eigenvectors? Well, I do the same thing. I find the null space. The matrix A minus I times identity. Okay, so that's a null space of the matrix minus I minus 1, 1, minus I. This might look a little unfamiliar, right? We know how to find null space of matrices with real numbers. We've been doing that for quite some time now. Yes, do you have a question?
Yeah, can you go back to the previous page?
Sure.
What is the thing like can do every what? I can't read.
I literally, oh, it says linear combination, span, row reduction.
No, I mean, before that, can do every something.
Everything.
Oh, everything. Okay, thank you.
So I'm doing like what I did after the first midterm. I said, oh, we never used that the vectors are actually in Rn.
Mm-hmm.
Now I'm saying, oh, well, we never actually used that the scalars are real or that the vectors are real. Everything we did actually works if the entries are complex as well. So I'm going to demonstrate. Is it okay?
Yeah, thank you.
Yep. Okay, so how do you find a null space when you do row reduction? Well, this is the pivot, right? I need to zero this out. What do I do? Well, I replace the second row as the second row, and I need to cancel this one. So how do we do that? Well, I can add the first row divided by I, right? because minus I divided by I is still minus 1. If I do that, so what do I get? So the first row doesn't change. This becomes 0. And here I get minus I plus minus 1 over I. Okay. Now here I need to do a little bit, I need to do a little check to figure out what 1 over I is. So what is 1 over I? Well, I can do this, I can multiply by I and I both sides. That's I over minus 1, which is minus I. Same trick as I did when I defined division. Yes, do you have a question?
Yeah, I don't want to keep bringing this up, but your mic does keep cutting out.
Oh,
like,
I'm so sorry. Okay.
Yeah.
Thank you for bringing it up. Yeah. Okay. So what that means is that this entry is just minus I plus I, which is 0. So actually this matrix is just minus I, minus 1, 0, 0, which is in row echelon form, a reduced row echelon form, actually. So actually, what does this imply? It implies that the null space, well, I mean, okay, how do you find the null space? You write the solution in free variables, right? So the solution set, which is, okay, the null space, that's this matrix, is going to be the same as the null space of this matrix of what's written above. So it's a set of all x1, x2, such that minus I x1 minus x2 equals 0. And this is a free variable, right? And well, that's just the span of, if you rearrange this, that's just the, another way of writing this is that x1 equals x2 over minus I. And that's just, we just figured out that 1 over I is minus I, right? So it's minus minus ix, which is x2, which is ix2. And so this is just actually the span of the vector I1. So in particular, what that means is the first eigenvector can be taken to be I, 1. And this is now a vector in C2, not in R2. So the price we paid for being able to always get eigenvalues is now our eigenvectors can be complex. And you know, you can indeed check that this works, right? So let's check that it works. This is the vector 1 minus I, right? Which is I times the vector wait a minute, I got this backwards. I put the minus sign in the wrong place, sorry. So this is minus 1 I, which is just I times the vector I1. So it is indeed an eigenvector. Okay. So it's the same algorithm. You just solve the equations and do row reduction, but now you may have to do complex arithmetic. The eigenvector turns out to be minus I and 1, corresponding to the eigenvalue minus I. And this is not a coincidence. So here's a general principle. general principle is that if AX equals lambda x for some complex eigenvalue and complex eigenvector, then the same is true if you take conjugate of all the entries. So where, you know, A conjugate is a matrix where you conjugate every entry. And X conjugate is a vector where you conjugate every entry of X. This is just an algebraic property of conjugate. If you conjugate an equation, it remains true, and you can just put all the conjugates inside the matrices. So in particular, well, here we know AV1 equals lambda 1 V1, or where lambda 1 is equal to I. So that implies that A bar V1, now A is real, so that's just A V1, A bar V1 bar, which is just A V1 bar, must be equal to I bar V1 bar. And, but now this I bar is just minus there, right? So this implies V1 bar, which is just minus I1, is an eigenvector with lambda equals minus, which is lambda 1 bar. Okay, so this is a way to save work, right? If you find one of the eigenvectors, you automatically get the other one just by taking a conjugate. So the summary is eigenvector come in conjugate. Okay, so any questions about this? Yes.
Wait. Why is the conjugate of A times the B1 bar equals to A times V1?
Are you talking about this part?
Yeah. Yeah.
Because A is real in this case. Okay, good. So I should write this. Yeah, I should just clarify this as maybe saying, in our example, A equals A bar. So this is true. Right? In our example, A is this matrix here.
Yeah, yeah. Okay.
Part of a real matrix doesn't change it. Does that make sense?
Yeah.
Okay. So that's a fact about complex eigenvalues. And what's the meaning of complex eigenvalues? Well, okay. Okay, so the meaning is, in some sense, always what happened in this example, right? So in this example, I pi by 2 counterclockwise. So the meaning of complex eigenvalues is captured. I mean, unfortunately, yeah, I guess I spent too much time on that permutation thing, and I won't have time to talk much about it. Let me just cite the theorem in the book, which does it. So this is captured in theorem 9 in the book. And roughly speaking, complex eigenvalues always correspond to rotation. In a two-dimensional plane. So, I mean, if you read the theorem in the book, it says that the theorem roughly says if A is a 2 by 2 matrix with a real 2 by 2 matrix with complex eigenvalues. So, by the way, if it has complex eigenvalues, then one of them has to be the conjugate of the other one. If they really are complex, i.e. not real, they must be distinct, right? Because there's two distinct eigenvalues. Then A is similar to rotation by some angle. Okay, and scaling. So what this is saying is if you have a 2 by 2 matrix with complex eigenvalues, it always corresponds to rotation. So in some sense, the example we looked at is the only example. And I'll just draw a picture to see what the theorem, to tell you what the theorem says. It says that if your eigenvalue lambda is equal to A plus IB, then this makes some angle in the complex plane, right? It's actually rotation by this angle theta in this picture here. Okay, so complex eigenvalue always corresponds to rotation. Okay, sorry, I didn't really get to everything I wanted to get to today, but I'll make some sort of supplementary video and continue next time. But any questions in the last minute or two? Yes. Oh, hello? Do you have a question? Yeah.
Yeah. I was just wondering, previously, eigenvalues were supposed to not change the direction of a vector. Does that change?
Yes. Okay, it's a great question. So here's a remark. And the reason is that we're thinking of direction in a different way, right? So, for example, consider the vector I, 1 in C2, right?
Mm-hmm.
Now, it is true that if you multiply this by I, that's scalar multiplication, right?
Right, yeah.
And now you get the vector -1 I, right?
Mm-hmm.
But you can't really say this is parallel to that.
Right.
So really what it has to do with is our concept of direction, right?
Mm-hmm.
So it's not parallel, but it is a scalar multiple. Right?
Yeah.
Of the original. So the following is still true if V is an eigenvector, complex of A. It is true that AV is still in the span of V.
Yeah.
But now
right.
and you're allowed to multiply by complex numbers.
Okay,
So
gotcha.
in this sense, it doesn't change the direction. But this is a different sense. C2 is really not a two-dimensional space, right? Because there are 4 numbers anymore. I mean, geometrically speaking. Because, I mean, you cannot visualize it as a two-dimensional space because there are 4 degrees of freedom. So this fact is still true, that an eigenvector remains, remains in the span of itself. Does that make sense?
Yeah, thank you.
Okay, well, any other question? Okay, well, that's all I have today, but see you next time.